Hello and welcome back to the module 3 of basic electronics, where we learned about the op-amp. Op-amp is basically a high gain differential amplifier, so that can amplify a wide range of signals, that is signals having a frequency ranging from 0 Hz to beyond megahertz. So this is what the op-amp symbol. So it has 5 terminals: inverting input terminal, non-inverting input terminal, positive supply and negative supply, and the output terminal. So we also learnt about the block diagram of the op-amp. So it is also the architecture of the op-amp and some of the characteristics of the op-amp. So we also looked into the equivalent circuit of the op-amp. So where Ri is the input resistance, which is the resistance measured between the input and the inverting and the non-inverting terminal. R0 is the output resistance. So Vd is the differential input voltage. So this differential input voltage is multiplied by the open loop voltage gain A. This A into Vd appears at the output. So output voltage is thus equivalent to A into Vd. So A Vd is a voltage source, so which is in series with the output resistance R. So ideally Ri is infinite and R0 is infinity, and the open loop gain is also infinite. So moving on to the next topic, another important is the Opamp IC. So Opamp IC 741 is one of the most popular and commonly used Opamp IC. So there are many manufacturers of them. Fairchild Semiconductor is one of them, so whose IC name is stated as mu A741. So it is a 741 is an 8-pin IC, so dual in-line package. So dual in-line package in the sense, on both sides of the op-amp we have the leads, so through which you can make the connections. Pin number 1 and pin number 5 are the offset null points, which are used to nullify the offsets and also provide the offset voltage compensation. So pin number 2 is the inverting input terminal, pin number 3 is the non-inverting input terminal, and output is taken from the pin number 6. So pin number 4 represents the negative supply voltage, that is minus VEE, and pin number 7 represents the positive supply voltage, which is plus VCC, and pin number 8 is a dummy pin to which no connection is to be made externally to this pin. Next we'll look into the ideal and the practical characteristics of the Opamp IC 741. So this table lists out some of the parameters of the op-amp, their values, that is the values for the 741 IC, which are the practical values, and also the ideal values of the op-amp. So the first one is the open loop voltage gain, so represented by AOL. So it's ideally infinite, but the typical value for the IC 741 is 2 into 10 power 5. So output impedance, the equivalent resistance, so measured at the output of the op-amp with respect to ground. So ideally it is 0 and typical value is 75 ohm. So input impedance is the equivalent impedance measured between the inverting and the non-inverting terminal of the op-amp. So ideal value is infinite and the typical value is 2 mega ohm. Input offset current. So this is the it is actually the magnitude of the difference of the bias currents. Ideally it is equal to 0 and typical value is 20 nanoamps. input offset voltage. So a small DC voltage that has to be applied at the input of the op-amp in order to force the output to be 0. So ideally it is 0 and practical value is 2 millivolt. Then the bandwidth. So bandwidth is the range of frequencies of the signal, so over which the op-amp performance is satisfactory. So ideally it is infinite. So this infinite value shows that the op-amp can amplify DC as well as the AC signals. So ideally it is infinite, so practically it is around 1 megahertz. CMRR, common mode rejection ratio, it is the ability of the op-amp to reject the common mode signal, so represented by rho. So ideally it is infinite, so practical value is around 90 dB. Sleeve rate, the maximum rate of change of the output voltage with respect to time. So this parameter shows how fast the output can change. This ideal value is infinite and the typical value is 0.5 volt per microsecond. And the input bias current, so which is the average of the base currents, so ideal value is 0, practical it is 80 nanoamps. Power supply rejection ratio, it is the ratio of change in the input offset voltage with the change or due to the variation in the supply voltage, that is one of the supply voltage with the other supply voltage being kept constant. So ideally it is 0 and the typical value is 30 microvolt per volts. Moving on to the next topic, the saturating property of the op-amp. So the supply voltages of the op-amp are plus VCC and minus VE. So these supply voltage decide the maximum output voltage levels of the op-amp. Practically, the op-amp output saturates at voltages less than plus VCC and minus VE. That is, once the output voltage reaches this level, it does not increase any further even if the input voltages are increased. So this is what called the saturating property of the op-amp. The maximum output swing of the op-amp is 0.9 times the supply voltages. That is, if the supply voltage, that is plus or minus VCC, is equal to plus 15 volts, the maximum output swing is equal to 0.9 into plus or minus 15 volts, which gives to be only 13.5 volts. Because of the saturable property, the open loop configuration is of little use in the practical applications. Saturable property of op-amp is useful in comparing the magnitude of the two voltages. Open loop configuration of the op-amp. So this is the simplest way to use an op-amp. So figure shows that the input voltages are applied to the two input terminals. AOL represents the open loop voltage gain. So the DC supply voltages are plus VCC and minus VE. So due to the saturating property, the voltage V0 is either at plus V saturation, that is plus VCC, or minus V saturation, that is minus VE, for a small input differential voltage. So the transfer characteristics. So transfer characteristics is nothing but the graph of output voltage versus the input voltage. So this figure shows that for a small differential voltage which appears at the input, so due to the high open loop voltage gain, so the output voltage varies linearly, and then the output also gets saturated at plus or minus V saturation. So for small range of input signal, that is from A to B, it behaves linearly, so after which it is the op-amp saturates. So thus, due to the high open loop gain, op-amp output is either at plus V saturation and minus V saturation. So this indicates the ability of the inability of the op-amp to work as a linear small signal amplifier in open loop mode. So that is, it is not suitable for the linear operations. So hence the open loop configuration is not generally used. So such an open loop configuration of the op-amp finds applications like the voltage comparator zero crossing detector. So that is, in other words, so for a small input voltage range, the output is linear. So after which it is saturated to plus or minus V saturation. So thus it operates linearly only for a small range. So beyond which it saturates. So thus it is not suitable for the linear applications. Okay. To overcome this, so the closed loop configuration of the op-amp is used. So closed loop mode. So this is the mode of the op-amp, so which increases the op-amp utility. So it uses a feedback. So the feedback resistor RF is connected between the output voltage and the inverting terminal. So since the feedback resistor is connected to the, that is the end of the feedback is connected to the inverting terminal of the op-amp, the feedback is said to be the negative feedback. So the feedback allows part of the output to be, the feedback resistor allows part of the output to be fed back to the input through the RF resistor. So in linear applications, op-amp is always used in the used with the negative feedback. So with the negative feedback, it controls the gain, that is gain which is infinite, that is open loop gain which is supposed to be infinite. So with the usage of the feedback resistor, so the gain is controlled. So thus the output is not driven into the saturation. The output is not taken to the saturation levels. So such a gain with feedback, that is the gain with the feedback, is said to be the closed loop gain, and it is always less than the open loop gain. So because of the reduced gain, so the op-amp is not driven into the saturation, and thus the circuit behaves in a linear manner. So it has got a number of advantages. So few of them are listed over here. First one is it reduces the gain and makes it controllable, reduces the distortion, it increases the bandwidth, it increases the input resistance of the op-amp, decreases the output resistance of the op-amp, also reduces the effects of temperature, power supply on the gain of the op-amp. Okay. Next topic is on the realistic assumptions. So there are two realistic assumptions that are made, so which actually helps in simplifying the analysis of the op-amp circuits to a larger extent. So the first assumption is the zero input current, that is the current drawn by either of the input terminals is zero, that is the current into the op-amp either through the inverting input terminal or through the non-inverting terminal is zero. Next, virtual ground. So this means the differential input voltage VD, that is between the non-inverting and the inverting input terminals, is essentially zero. So here we have a circuit with the negative feedback, op-amp circuit with the negative feedback. So wherein the input Vi is connected to the inverting terminal through the resistor R1. So non-inverting terminal is grounded, and a feedback resistor is connected between V0 and the inverting terminal. So because of this feedback resistor, a part of the output is also fed back to the input, that is to the inverting terminal. So since the input is connected to the through the inverting terminal, so output is inverted. So hence the output which is fed back is in antiphase, that is in opposite phase. So the voltage at this point, that is at node A, so will cancel out each other. Okay, that is V1 and a part of outputs which is in antiphase, that is which is of opposite polarity, though they tend to cancel out each other. So hence the voltage at this point appears to be equal to 0. So and this V2 is connected to ground. So because it is the differential voltage is equal to 0, so it states that V1 is equal to V2. It can also be proved that, so since the open loop voltage gain is infinite, okay, so due to the very large gain, a small output voltage appears. This output voltage is very small, so thus because of the high loop gain, high open loop gain, so the differential voltage Vd would be equal to V0 by infinity, so which is approximately equal to 0. So since Vd is the difference of the two input voltages, that is V2 minus V1, and since it is equal to 0, so V2 equal to V1. So since the voltages are equal, so we can say that there is a virtual short between the two input terminals. Virtual short is there is no physical connection between V1 and V2, so thus it is the virtual short. A short exists which is virtual in nature. And also that since I equal to 0, that is current drawn into op-amp is equal to 0, the current which was flowing through R1, so same current flows through the RF resistor as well. So thus I2 is equal to I1. So in other words, so we can state that if the non-inverting terminal of the op-amp, so as given here, if the non-inverting terminal of the op-amp is grounded, by the concept of virtual ground, the inverting terminal is also at the ground potential, though there is no physical connection between the inverting terminal and the ground. So this is what the principle of the virtual ground. Okay, so these two realistic assumptions are very important, as they are the one on the basis of which the voltage gain expressions are derived for the op-amp application circuits such as inverting amplifier, non-inverting amplifier, summer circuit, integrator, differentiator. So all these circuits, for all these circuits, the voltage gain is derived, so starting from these basic assumptions. So thus in the next video we'll see the applications of the op-amp. Thank you.